Okay, so I think that was a really good talk to go in front of my talk. So what was really interesting in Douglas's talk is to me, was about the problem of optimizing software at massive scale. I deal with a lot of people who can optimize very small bits of software. And, you put a lot of effort into a very small bit of software, but when you're dealing with software written by scientists and experts in a different field, being able to solve that problem at scale is really important. Is this working? Yep. And the other thing that came up a lot is about accelerators. So that's going to be two themes from my talk. But this is about building the foundations really from the lower level. So I'm the founder and CEO of Codeplay. I'm going to talk a little bit about the history, actually. Founded in 2002 in Edinburgh in Scotland, and we specialize in compilers for accelerator processors, such as GPUs, but not just GPUs. And we were acquired by Intel last year, in June last year, but we still exist as Codeplay, and we've still got quite a big picture vision, which is what I'm going to talk about building this foundational technologies across the industry. So I actually was a video game developer. And the reason I bring this up, parents, is a 3D video game that I did a long time ago on an 8-bit computer. And in the early days of video games when we were doing this is a Z80 processor on a ZX Spectrum, I think, which is why all the colors of the balls don't quite work. We were using much older processors from much older business systems. We were using the things that were obsolete for everyone else. And that's changed because the supercomputers in the exascale computing program are using graphics processors that originally come from video games. And the other thing that we had is that we had years to squeeze the most performance out of older processors. So when I was writing this, I could spend a lot of time writing everything in assembly language. Had a lot of documentation about the processor. A lot of people had done stuff in it before. And so I could really focus on how do I specifically get performance out of this specific processor. But when we're designing software for a supercomputer that doesn't exist yet, actually it's very different. You don't have the hardware at the time you're designing the processor. So you actually have to do the optimization work in advance of getting the hardware. And that's a big difference, really. It makes a big fundamental difference about your thought process from being able to spend a lot of time tuning something for something that you understand versus writing software for hardware you don't yet have. So what has changed over the years? In the 90s, people we'd spend lots of time writing video games for these 8-bit processors, and then in the 90s, people discovered that what you could do is you could write a game on a PC, doing things that were never possible before, like new 3D graphics, and it would actually be really slow. So you'd write a game, and you'd go, this is super slow and unplayable, and people would think that's a stupid thing to do. Why would you write a video game that's super slow and unplayable? And by the time you'd finished writing the video game, there were new CPUs out that ran that video game at really decent performance. And so the smart thing to do was to write software that you couldn't currently run, because all of the people buying the new processors and the new PCs wanted to run the latest software. And so the PC overtook the games industry and became the engine of innovation. And it was because you could write something in advance and then you'd be saved. I remember there was the famous talk, The Free Lunch, by Herb Sutter, talked about the free lunch. It was a free lunch, right? You'd write stuff, it was too slow, and the CPU designers would make things go faster for you. So this is me quite a while ago. I decided I wanted to be part of driving new ideas in technology, and it became clear in the 90s, late 90s, that as these new technologies were coming into the video games industry, the video games industry was going to start leading what then happened. I suppose I was a bit surprised that it ended up in supercomputers doing earthquake science or medicine or things like that. But that's what I was interested in. But what it did mean is that we were going to have to write software today on the new processors that are going to come. The only way it was going to work if you are doing something innovative is if you could write the software today and then run it faster on new processors, and that requires compilers. So Codeplay is a compiler company. So what is a compiler? A compiler takes computer source code written by a programmer and turns it into instructions that a processor can execute. But if we turn that question around and say, well, what is actually a compiler for? A compiler enables programmers to write code that does what the user wants. So what's very strange about this, it took me a while to realize this, is what a compiler is for is actually the opposite of what it does. The purpose of a compiler is to create the input. Most software, right, you give it the input, here's my data, you pass it into the software, and you get the answer. A compiler is quite unique in the sense that the purpose of the compiler is for the programmer to construct the input that's going to give you the output that you want. What it means is that building a compiler is actually quite a small part of what a compiler company ends up doing if it wants to be successful. If it wants to be successful, a compiler company needs to focus much more on enabling people to build an ecosystem. And this is all the stuff that was in the previous talk. So you need to enable people, much larger teams with a variety of skills. You know, people who understand earthquake science or AI or medical diagnostics need to write code with your compiler. They're not programmers, or they've learned programming, but they're fundamentally some other kind of scientist. I mean, this is kind of what happens in video games, right? Some people are hardcore programmers, but some people writing video games are much more interested in, is the game fun, or does the game look good? You know, you're much more interested in how it looks or plays or something like that. So that variety of skill set, you need to enable people to do that. And so that means that a compiler company actually ends up spending more of its time on things like training people how to write that source code than they do on actually compiling that source code and running it on the hardware. And you do have to work out how to target a variety of different machines. And I often get told, oh yeah, but if you target multiple machines, then actually that's going to make your code go slower, but that's wrong. Because you have to be able to target the machine that doesn't exist yet. That's how you get the performance. You always have to think about the future machine. Otherwise, you're not going to get the good performance. You're going to get efficiency on some old bit of hardware, but you have to enable people to write code now for the machine that's going to come in the future. And to do stuff at scale, like real-world software, you have to integrate a lot of different components. That's also what we're looking at with the exascale computing program. There's all of these different components that have to be integrated together in order to be able to run the software at scale. And one of the things that happens then is you end up standardizing the language to enable people to write once and then use many compilers so that they can switch from one compiler to another compiler as they go on to the next bit of hardware. And that, once you get involved in standardization, means you have to work out what the IP rules. If you're asking people to develop software for your language, you have to explain to people what are the legal rules around this. These are all the things that you don't really think about when you're building a compiler, but actually it's very important. If we don't work all of these things out, then the compiler doesn't serve its purpose. It's interesting technology, and I deal with lots of people who write compilers that are interesting technology, but they don't serve its purpose. So if we want our compilers to enable us to build these new supercomputers, we have to do all of this other work, which is actually more than the small team of specialist compiler developers just writing the compiler. So what is an accelerator processor? I always find it interesting that we talk about accelerator processors, but it kind of always ends up being graphics processors. It's my video games background again. I often ask, why does it end up like this? And the answer is, it's because in video games, you know you need an ecosystem. you don't have an argument, right, about this. If you're building a video games processor, you know that there are video game developers out there who are going to write video games, and you have to enable them to write the video games for it. Whereas in lots of other cases, people will argue that they don't need an ecosystem, they just need a processor for a specific thing. Anyway, it's an interesting thing. So early computers did everything with a CPU. So when I started, I lived here in Auckland, actually, and I had a ZX81 here in Auckland. The ZX81 used the CPU to drive the TV. So while it was outputting the signal to the TV, it couldn't do any processing. The Z80 actually did everything. And then what happened is computers added lots of special hardware to be able to drive the monitor and things, but it was quite fixed function. There were fixed things that you could do, and so that's why I wrote a tennis game, and you had these tennis players that moved around, but we had to draw all the tennis things. It was, but the hardware was doing this very fixed thing, and the hardware designers had designed what it is they were going to do. But by the early 2000s, the graphics processors, called GPUs, had become fully programmable. And what that did is, it comes back to what I said before about enabling people to do new things. When the GPUs became fully programmable, it enabled the people who knew about graphics to do really interesting new things. And so the whole field of graphics in video games, it's incredible the way that they simulate light and the effects of different lights and reflections, and a whole lot of study goes into it. That, you know, you have specialists in that field who are able to do it. That's what happens when you enable programmability. And enabling programmability for those GPUs meant people had to work out all the stuff like how do you document it, how do you train it, how do you standardize it, how do you work out how you can write GPU code today and it runs on the games console of tomorrow. So what we end up now is the idea of the CPU and the accelerator processor. And mostly the accelerator processors today are GPUs, because GPUs are ready to handle the ecosystem. I don't see that there's any reason beyond that organizational question, is how I see it, of why it's a GPU. Right? GPUs are optimized for graphics in video games. You get a slightly different version of it if you're building a supercomputer that costs about 10 times as much, I think. But it's not that different. It's just that fundamentally, you know, from a software point of view, you've got an ecosystem, but you end up having GPUs because everything's set up to do things with GPUs. So at the moment, if you look at what's happening in the industry, you'll see there were CPUs, which are still great at latency-sensitive tasks. So if I press a key on the keyboard, the GPU is terrible at responding to that and making something happen. Yes, it's good at displaying something on the screen, but a GPU is a really, really terrible processor for quickly reacting to something. And CPUs have a huge, well-developed ecosystem. Everything I've talked about is kind of irrelevant if you're talking about CPUs, right? Because people have worked out how to do that. GPUs are great at graphics, and that means that they're great at processing lots of floating point data, and they have a huge, well-developed ecosystem for graphics. But there was a single vendor ecosystem for non-graphics data-intensive applications. And that's one of the things that the XScale computing project had to deal with, is that all the software was originally written for NVIDIA GPUs only in CUDA. So we have to spread that out to enable multiple vendors in the GPU space to do that. But there are other processors that are great at specific tasks. Especially if you use something like your smartphone, the CPU and even the GPU are not actually that big on the chip. There's a whole lot of other processors doing amazing things. They have a much longer time to market, those processors, and there's no open ecosystem for the software. So most of the compute capability that's in a system on chip that would go into something like a smartphone is not really available to you as a programmer. It's quite weird if you think about how in the past, almost everything was available to you as a programmer. You could use the whole performance of the system. But today, if you're going to write software for a system on chip, you might well be able to write it for the specific generation of chip that you've got in front of you, but it's not going to work well on the next generation of chip. There's no backwards compatibility. And those other processors are really struggling to keep up with new innovations. So there's lots of AI processors, but if you look at the AI chip vendors, they have stunningly tiny revenues. All of the AI chip vendors have massive amounts of investment, and you can look at some of the numbers now, right? They're getting very, very little market adoption, and they're running quite old networks. They're not able to run the latest advances. So if you want to be able to develop the new model, they don't appear first on the AI processors. They appear on GPUs first. So we've got a challenge to fix, right? Accelerators give the performance we need for future software innovations, and we can adapt accelerator processors so they're not just GPUs. They could be optimized for other kinds of workload. But if we don't enable an accelerator ecosystem, all of that other stuff that I was talking about, not just building the compilers, all of the other stuff, the standardization, IP models, all of that stuff, then we can provide performance. We can provide incredible performance with hardware, but it's not going to enable software innovations. It's not going to enable people to design new neural networks. It's not going to enable people to do self-driving cars, and it's not going to enable people to do all of this incredible science that's being done in the exascale computing project. We've got to solve the ecosystem problem for these accelerators. So the challenge we have today is if we look in the accelerator space, we have the AI graph compilers that come from the AI chip companies that just are not achieving much market adoption. They give interesting performance results, but when you come to do work with them, they just don't solve a customer problem. They solve a proving the performance of my hardware problem, but they don't solve a customer problem. They don't allow an innovation. We've got single device programming models like GPU programming models, but those are not enabling people to do hardware innovation. If somebody was saying, I want to look at all of the software that's being developed by the scientists and the SYCL computing program and all around the world, all the scientific software, and now what I want to do is I want to design a processor that isn't a GPU but is really good at running that software, it's very difficult. It's actually very difficult for someone to actually design something that isn't a GPU that's better at running some of that software and enables new innovation. And the last thing is that we have a lot of CPU-only programming models that are not very good at accelerators. And again, that's blocking innovation because CPUs are not going to give us the big improvements in performance that we need in the future. So we've got to get out of these systems that are closed in a way that blocks the innovations that we need to make. So if we look at the solutions, actually, once you start looking into the details of it, we know the technology answers, right? We know that there isn't one solution for everyone. So when we looked at all the scientific software, there were lots of different frameworks. People were trying to have common features within different frameworks, but there's not. You can't just say to everyone, you have to program like this, directly using this hardware without using any middleware, without using any libraries. That's just a crazy solution. You need to be able to have that ecosystem of different components that integrate together. But we know what they are. We actually know what systems are working today. And we do know the organizational answers. We know that standards bodies, for example, are the way to do things. You know, I do find it very interesting that the first compiler was developed by Grace Hopper. I think she was asked to do an assembler, and somehow it went a bit further. And it was obviously revolutionary for software, because suddenly it allowed more people to write software, and write software that moved from one bit of hardware to another. But she ended up running the COBOL standards body, the first programming language. It's just right from the beginning of compilers, we moved smoothly into the standardization process as being the solution. So we know that industry standards and we know that open source projects can deliver these ecosystem-friendly and innovator-friendly platforms for innovation. But we do have to do the work. It's not just the technology of just, look, I can stay in a back room somewhere and I can write my own compiler. We do have to do all of this other work to enable the organization to build an ecosystem. And you know, one of the things always gets me is, you know, hardware moves much faster than software, or at least hardware abandons things much faster than software does. It's very hard to get rid of legacy. My laptop, actually this one doesn't, does it? But my laptop is Windows, right? It's got a C drive. What happened to the A and B drive? I remember them. I mean, I'm the kind of person who still has an A and B drive, actually, on my laptop. Not on my laptop, on my computer. But why have we still got a C drive? Why has nobody been able to get rid of it. If you look inside, even in Windows today, it's got MS-DOS and stuff in there, which is based on CP/M, which has these 8+3 character file names, and everything still works like that. All of that backwards compatibility needs to be maintained. So success for hardware ecosystems comes over decades of building up a consistent software ecosystem. So we need to make a plan that's going to last for, well, Intel, who I now work for, their CPUs go back 40 years, right? The instruction set is 40 years or more that they've maintained some level of compatibility. That's what we've got to do. We've got to build that long-term ecosystem backwards compatibility for the future. If we want people to build software, we've got to promise to them that when they finish designing their software, which may take 1, 2, 3, 4, 5 years, that software is going to run on that hardware of the future. So we've got to set ourselves up for the next 40 years of software. And so that's why I was very involved in the SYCL standard. I chaired the SYCL standard. Now very involved in OneAPI, which is an extension of the SYCL standard with a whole ecosystem around it. People ask me about other languages. It's not just about SYCL, it might be about Fortran and other things. I actually pushed very hard for the SPIR-V standard, which is an intermediate representation that allows you to design your own programming language for GPUs, and people use it in Rust and various other languages, use the SPIR-V standard. So we use all of that within OneAPI, and what we're doing now is we're building the software approach for decades to come. And what we're doing is we're choosing the best-in-class components to go into this ecosystem. And I use the word we rather than Intel or Codeplay, because this talk is really a call to action. We're going to involve a lot of people in this. We're bringing people in. We're opening this up to a form where people can put in the best-in-class industry standard approaches and review them and then be able to support them over the next 40 years. So I thought I'd then go into some of the technical details of what this means and why you have things like SPIR-V and what it actually means, why we need to change stuff. So a CPU compiler, like C++ or Fortran, has a compiler front end. It then goes optimization passes and then code generation, and then goes down to the CPU ISA, the instruction set. So that's why what CPU companies do is, instead of maintaining languages over 40 years, they maintain the instruction set. So Intel and ARM maintain the instruction set over a very long time, and then the compilers can change. So what happens if you've got a heterogeneous system and you're sticking in GPUs or other kinds of accelerator processors? Well, we still have a compiler front end, and we still have optimization parsers, but now we have to split that code and go down to parsers. And so we have CPU code generation that goes down to a CPU instruction set, an ISA, and that CPU instruction set, the ISA, is going to be maintained over a very long period of time. But actually what changes is, for the accelerators, we don't maintain the ISA over long periods of time at all. It's very unusual for a GPU company to maintain their instruction set over a long period of time. So now we have to make that commitment at a higher level in the stack. It changes the way we have to work. We are not going to have a GPU vendor committing to maintain an instruction set for the next 40 years. It's not going to happen. And new kind of accelerators being invented, that commitment is not going to be based around the ISA. It has to be based around something higher up the stack. So that's why we need something like OneAPI, which is more of a hardware interface, and SYCL. And then the other thing is, it's very important in a heterogeneous compiler, is that we have a whole load of software which is not a compiler, that's handling all of the data movement, which is another thing that came up in last talk about how important we need to reduce the data movement and keep data on the GPU as much as possible, or on any accelerator. The data movement in modern systems is much slower than executing instructions. You know, I remember back on my ZX81, right? If I wanted to do a floating point multiply, that was like thousands of instructions. And if I wanted to read from memory, it was like one instruction and one cycle, right? It's not like that anymore. It's thousands of cycles to read from memory, and 1 cycle, in effect, to do a floating point operation. So this is why what we do now is, for some reason there's no SPIR-V logo, there's a SPIR logo because it's the first one, but anyway, we don't maintain the CPU instruction set. We stick this SPIR standard in, and that is an intermediate representation that allows us to have the accelerator code generation change for different accelerators. So instead of using the ISO, we use this SPIR-V standard. So there are these new technologies like MLIR, which is very interesting, but MLIR is not the interface between the hardware and software. What it is really good at, MLIR, is it's a modular set of compiler passes that you can plug in that do a lot of the optimizations for you. And that makes it much easier to build these software stacks for new hardware. The fact that it's modular, you can just pick and choose the bits that you need to go into your compiler stack. So instead of having to understand all the different parts of the compiler stack for your hardware, you can use MLIR. And I see people going, oh, we've got this problem in the compiler, I don't know how to solve it. I just pull this MLIR dialect, it's called, and some software, and fit it in. And it makes it a lot easier to stick those compilers together. And then the other thing that we've done, I noticed a lot of code was being moved from Fortran to C++, and that's why we did SYCL. So the SYCL standard is, in effect, it's the C++ of accelerators. And remember I said we had to work out all the legal details. SYCL is royalty-free, vendor-neutral industry standard. It's got a standards body, Kronos, that manages it. And you can go off and implement it, and there are a bunch of rules about what you have to do in order to implement it, but you can implement it yourself, and multiple people do. And you can use it, and you can write software in SYCL, and you can use that C++ style. And why is that C++ style so important? We designed SYCL to enable you to write all of those frameworks. So those middleware frameworks like Cocos and Raja and various others, they use C++ techniques that in effect allow you to do lots of things in the compiler without having to write a compiler. You know, lots of people try and fix a problem in a compiler, and turning a C++ problem, which can be a little bit tricky, into a compiler problem makes it much harder. And so we designed SYCL to enable people to design those kind of frameworks that then make it much easier to get performance at scale. So now we can build our own C++ SYCL compilers for a variety of new processors, and we can design our own optimization, and we can build those C++ frameworks. And it's still native compilation, in effect, that you're actually compiling for the hardware. I don't know if I have enough time to do this, but in SYCL what we do is we handle the parallelism via parallel 4. The way this is done is, I don't know if you can see, there's these square brackets around the equals things if you're unfamiliar with modern C++. Since C++ 11, we've had this thing called lambda functions. And lambda functions allow us to make it look as if we'd written a for loop using the syntax of the language, and we haven't. We've written this entirely using standard C++. Parallel 4 is a function. It's a templated function inside C++, but it looks like it's built into the language. And that's why we were then able to implement Parallel 4 in a way that's efficient on lots of different hardware. And so we can use standard C++ compilers when we're actually using this. We still need what's called a device compiler for the hardware, but in general we're using standard C++, and it makes it much easier for us to integrate into existing tool chains. And then what we've done inside SYCL is we force people to use these accessors. You don't always have to use them anymore, but the older versions of SYCL force you, now it's optional. But the accessors, what they do is they allow you to customize SYCL for hardware that accesses memory in different ways. So a lot of hardware will not just allow you to just load any old memory just like that. It will require you to use DMA and various things. These accessors allow us to make small changes to our code. We just change the accessor, and it can go much faster on particular hardware. So that's why what enables SYCL to target a much wider range of hardware with a wider range of memory systems, because remember I said memory can be 1,000 times slower than compute. If you optimize the memory system, SYCL enables us to do this. So we've thought very hard in SYCL about how we enable innovation in hardware design. And this is what we maintain throughout it, so that you can actually innovate and design new hardware and map it to SYCL. And I'm going to skip over this because I don't have much time. But so the other thing that I do always have to say with SYCL is, what if you've got some processor with some special hardware, and I know that this processor can do this one thing, so I want to get the maximum performance on the processor that I've got. SYCL is a baseline on top of which we have extensions for each different processor. You can add your own extensions. It's not like Java where you're not allowed to extend it. We allow you to extend it. That's in the rules of the language. And so if you're working on one GPU or an FPGA or some other accelerator, then you can use that in your code, and then you use those C++ framework techniques to hide the difference. So you can still write code that uses, I'm running on a GPU from this amazing new vendor here. I'm going to use that feature that makes it go faster on that GPU, or if it's not running on that GPU, then you can go back to normal SYCL and not use that feature. So we still enable you to do those intense optimizations, but we allow you to hide them inside frameworks. So that your scientist writing their application doesn't need to know about it, but the optimization developer working on the framework does. So, lots of promise. What are we actually doing to build it? So SYCL started as a Codeplay project, but we worked with a lot of collaborators. We brought people in. It's very much a community project. It became a community project. And SYCL was a project to build out an ecosystem for C++ on accelerators. But SYCL is now led by all of the people who join. I was the chair, not anymore. So it's led by the people who join. It's led by scientists and machine learning engineers as well as hardware people. And so it became the product of experts in our field coming together. And that's what makes a standard successful. You want all the different experts coming together, designing something that's going to work together. And that's what we're now doing with One API. One API started as an Intel project, but we're opening it out. So we're going to work with collaborators to build out an even wider ecosystem. So One API is open source, slightly different from SYCL. It's not a multi-vendor specification that you go off and implement yourself. You can. There is a spec, but there's also an open source implementation. So we can manage it as more of an open source project. And what it includes SYCL, it includes Spear, but it also has a lot of libraries that you can then customize for your hardware and software. And it is a growing, constantly evolving open source ecosystem. So One API is now going to be led by all the people who join. It's going to become an industry initiative that's led by the people who join, and it will become an open source project that's led by the people who join. And we're going to bring together both the hardware and software innovators to build out a truly open industry-wide ecosystem for accelerator hardware and software. It's not just about GPUs. You can go off and design your own custom accelerator and get the advantage of an ecosystem. So we're going to, this year, we're going to move it into a new open organization. We're inviting people to join up to become part of that. It's going to be structured as this constantly evolving open source project that takes in feedback from users, and it will enable a wide range of hardware, and that will grow over time. There'll be more hardware. We've proven that SYCL and One API features can work on everything from GPUs to FPGAs. At Codeplay, we've done some quite extreme processors and proven that it works. But it's not just about SYCL, right? That's why SYCL isn't in the One API name. SYCL is part of it. It's going to enable a wide range of software and other languages. And other languages can either become part of the project or they can build on top of the project. So it's going to grow. And we're also doing a lot of work on integrating One API and SYCL into frameworks that are in HPC and AI. So if you're a hardware vendor and you adopt One API, you're actually going to be able to run a lot of software. The software that's being developed with One API today will be able to run on new hardware, and you will be able to optimize it for your hardware as well. So come and join us. You can join One API and help shape our future. Today, it's not a fully legally constituted organization. We're working out what that's going to look like with partners. So you can join it for free. I don't think there's even anything you have to sign at the moment. We probably will have to work out a lot of that legal structure. And you can download pre-built binaries of One API for Intel, NVIDIA, and AMD GPUs, so you can try it out and run it. And it's all being actively developed. And you can bring your own hardware and software. So that's it.